Jun Ueki, please start.
Yes. Oh, thank you for introduction, and thank you for letting me join this conference again. I visited your country 3 years ago, and I love the place, the culture, and the people. So I'm happy to see you again. And every day I'm watching the TV news and following what is going on in the world. Um, yeah, I hope to visit there and see you all again. Yeah. Now let me start my talk. Um, I'd like to talk about recent progress in your society for notes and links. And this is joint work with several young people in several universities, Waseda, Tokyo Science University, and Nagoya University. And yeah. First of all, I'd like to explain something on profinite rigidity. Let K be a knot that is the image of embedding of the first one sphere into 3 sphere. And let pi k denote the knot group. And let pi k hat denote the profinite completion. That is the inverse limit of the finite quotients. And here is a very interesting question. What does the set of finite quotients of pi hat know? It is equivalent to say that what the isomorphism class of the pi hat know. This is indeed very subtle question, but recent days there are much progress due to borrow freedom, Blitzson Reed, Wilkes, ED, and many other people. My main interest is the Alexander polynomial. Let pi k note that the abelianization of pi k is isomorphic to z. Let t denote a formal generator of z. And this kernel of this map corresponds to the z cover. This the maximal abelian cover. And let x infinity denote the z cover. Then its first homology group is a finitely generated torsion ZTZ module, and its fitting ideal is generated by Alexander polynomial. In addition, let pi k to z over nz denotes the natural surjective homomorphism. Then its kernel corresponds to the z over nz cyclic cover denoted by xn. Now, the classical Fox-Weber's formula asserts that if the Alexander polynomial does not vanish on nth roots of unity, then the size of the torsion subgroup of the nth cyclic H1 of the nth cyclic cover xn is given by the cyclic resultant of the Alexander polynomial. Or in other words, it is the product of the value at each nth roots of unity. We may easily see that this torsion subgroup is determined by the isomorphism class of the pi profinite completion pi hat. By Fried's Fried theorem, together with my proposition asserting that a cyclotonic polynomial is a unit in GPTZ hat. We see that in the following theorem. And the Alexander polynomial is determined by the isomorphism class of pi hat. We may further ask about a concrete detection and Pro-P detection. This is section 0 about profinite completion. Now I move to the theory on twisted Iwasawa invariant. Let K be a knot in S3 and P a prime number and M an integer which sorry, N a integer which does not such that P does not divide M. And OP over ZP are finite extension of the ring of periodic integers. ZP is defined as the inverse limit of cyclic p powers groups. And let rho be a representation of the knot group. Then we have the twisted Alexander polynomial, defined as as a generator of the fitting ideal of twisted Alexander module, twisted by rho. Now note that periodic Weierstrass preparation theorem, very basic tool in number theory side. There exists some integer mu and nu such that the polynomial coincides with this guy up to multiplication by units. In the formal power series ZPT with quotient ZP. This is theorem. For this mu and nu, there exists some nu such that for any sufficiently large n, this equation holds. And this mu and lambda here, this mu and lambda are mu and lambda here. This asserts that NPN's cover the twisted homology of NPN's cover the torsion is given by in a uniform way. And these invariants are called Iwasawa invariant of rho. These invariants are of great interest in number theory side, and there are many studies. In knot theory side, I think this is the first time to define and study these invariants for representation. But there are some interpretation of these invariants. Mu is indeed coincide with the Bowen's periodic entropy of the meridian action on the twisted Alexander module. In number theory side, mu equals 0 is a big theorem or a leading conjecture. In knot theory side, and there should be, we may have some interesting question. In regards with lambda, we may expect that lambda is related to genus of knot. We may today we say yes for this. We answer yes for this question. Why we may expect this? Because in the number theory side, we have an analogy between number fields and function fields, and lambda of ZP extensions and genus of Riemann surfaces. In the sense, this analogy was pointed out by Iwasawa and Kida. Indeed, he pointed out that Kida's formula on lambda invariant is an analog of Riemann-Hurwitz formula for covering of Riemann surfaces. Here are our another theorems. For any rho and p, there exists some m such that the lambda over the extension degree coincides with the degree of the Alexander polynomial. Furthermore, there exists some rho such that this coincides with the genus of the knot. We also have the following. For any rho and p, if m moves, then lambdas and mu's determine whether the twisted Alexander polynomial is monic or not, and whether k is fibered or not. And these theorems are all based on Friedel reduces a very deep theorem on deep study on twisted Alexander polynomial. And they are just a translation of their theorem. But we may obtain several interesting questions from these translated version. And there are some examples. Let K be the twist knot. Twist knot is defined for each integer, small k, and defined by the following diagram. And this series contains popular elementary knots, a knot, trefoil, figure 8 knot, and first non-fibered example 5.2. And it is known that this is fibered if and only if k equals to 0 or plus minus 1. We proved that by a concrete calculation that for any row to SL2, mu invariant is always 0. But Friedel reduces another theorem asserts that if k is fibered, asserts that k is fibered if and only if there exists k is non-fibered if and only if there exists some residual representation with 0 Alexander polynomial. So if we find such O and if we take a generic lift to a ZP, then we may expect that we have positive mu. So, but at this time, I have no example of such, no concrete example of such row bar and row. So I'm really eager to find such row with a row with positive mu. This might be very suggestive for number theory side also. So please let me know if you have any hint for this question. I also would like to remark another example, and that is the lambda invariant of the lifts of holonomic representation of the figure 8 knot. I just remarked that lambda of rho plus and rho minus does not coincide. So it is remarked that by Dunfield Jackson that the holonomic twisted Alexander polynomial of the holonomic representation has many much information about knot. So it should be interesting to study what the invariance of holonomic representation of hyperbolic knots know. And so yeah. Our paper about this story is on the archive. So if you are interested, please look at this paper. Now I'd like to explain something else. This is about Weber's class number problem. Let Kn be the cyclotomic extension of Q. Then it is conjectured that and expected that its the size of the ideal class group is always 1 for any p and n. But it was initially pointed out by Weber more than 200 years ago. But in this modern time, we still only know that, for example, if p is 2, then this is yes for n equal 1, 2, 3, 4, 5, 6, 7, and unknown for larger n's. So it is interesting and very difficult problem. In the not theory side, on the other hand, we can study more with many topological tools. for example, let K be a knot in S3. Then Livingstone previously proved that for any P powers, for we have this group, the size of this group is 1 for any prime powers, if and only if that is the classical Alexander polynomial is the product of several cyclotomic polynomial, where m is divisible at most 3 distinct prime numbers. In the number theory side, we recently, very recently, Yoshizaki-san pointed out that ideal class number converges in the periodic integer ring. And in the not theory side, I and Yoshizaki-san recently proved that for a not k and any fixed prime number p, this value converges in the p. For example, and we can explicitly calculate for several examples. For example, if k is the AB torus knot where a and b are coprime integers, then so we may we have the symmetricity in A and B, so we may assume that B does not divide B. And we may further, and if we have this, then the limit value is given by this guy. This is just proved by the fact that its Alexander polynomial is a product of several cyclotomic polynomials. And then by using Apostle's study on the resultants of cyclotomic polynomials. And we have further theorem. For example, let delta kt be the following form. And we note that if alpha, the size, the periodic norm of alpha I is 1, then there uniquely exists p primes roots of unity with which is close to alpha. And we just assert that we found that the limit value is given by such roots of unity. For example, if k is the twist knot, then we have Alexander polynomial in this form. And if p does not divide k, then we have that the limit value is coincide with a certain root of unity in the p. And if p divides k, then we have that the limit value is 1. We have many further questions. And one of the most interesting might be that generalization of Livingstone result for such limit values. I have just one more page. And this page is about the product, ZP product extension or ZP product cover. Kokomonsky proved an variant of Iwasawa's class number formula for ZPD extension of number fields. And now let K and we formulate its analog for links in S3. Let L be a link with D components. Then it's the aberranization of the link group is isomorphic to ZD. So we have a natural surjective homomorphism to Z over NZD. And this corresponds to a certain finite cover. Our theorem is the following. There exists some mu and lambda such that for any sufficiently large n, this equation holds, where O1 is the Landau notation. And this is proved by Monsky's analog of periodic wireless preparation theorem. And we also use some standard argument. In order to calculate examples, we also use Maybelline inequalities formula. I just remarked the examples. The first one is Solomon's one. If P is 2, then this value is given in this way. And if P is not equal to 2, then it is always true. So we have O1 part, constant O1 part. Another example is a twisted white-head ring defined by this diagram. It's like masked guy. We have Alexander polynomial in this form. So we may see that this example realize any mu. Finally, I'd like to remark that in the number theory side, Kokomonsky remarked that this O1 part can be non-constant. But I think there is no concrete example yet. In the topology side, it must be interesting to find an example with a non-constant O1 in topology side. But in this case, we need to replace S3 by some rational homogeneous sphere. I just have one more remark to finish this talk. Professor Morishita, my supervisor, told me that S1 varied Morse theory is Iwasawa theory. I don't know why, but it must be an important, interesting question to find what this means. And that's all. Thank you for listening.
Thank you very much.
Thank you.
Any question, please? Do you have any question? Yes.
Can I ask a question?
Yes, please.
So you gave some examples about twist knots and twist links.
Yes.
Can it be extended naturally to two-bridge knots and two-bridge links?
We haven't yet tried that, but it must be the next concrete problem.
Concrete one?
Yeah, and this theorem is applicable for any not with any if the Alexander polynomial is known, then we may apply this theorem. But I don't know.
So
We don't still have we don't have yet a good formula.
But then will it be interesting? It seems like it can be extended.
Yeah, yes.
Okay, thank you very much.
This concrete calculation is indeed quite seems quite difficult in general. So I'm not sure if I can find.
Okay.
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 Okay. Thank you.